us have gathered in this hall, and some of the participants have also joined online, as you can see. So we thank each of you for your participation. We are also very delighted to have with us in this hall some renowned professors, Professor Devshankar Rai, Professor Shamal Bodro, and many others, who have more than 40 years teaching and research experience in quantum science and related areas. I don't see Professor Sanjeev Ghosh. Is he around? Okay. And some of the participants have joined us online. Among them, we have Professor Subhashish Dattagupta. Subhashish, welcome to this discussion meeting. He is joining from TIFR Hyderabad. And also we are very pleased to have the director of Essenbosch Center, Professor Tanushree Shah Dasgupta, with us. And also we have participants from TIFR Hyderabad, Professor Harish Krishnamurthy, and Professor Amit Rai from JNU, and Professor Surajit Sen from Silchar. So with this, I would like to once again welcome you all, and we look forward to your active participation in this meeting. We have a plan to write a white paper on teaching curriculum in quantum science and quantum technology based on the outcome of today's discussion. So I request you to give your valuable opinion and suggestions on the topic of today's discussions. So with this, I hand over to my colleague, Professor Nirmala Ghosh.
Thank you, Vinodendra. So first we'll have basically brief presentations by Professor Bodhaditya Satra, IIT Delhi. He'll be talking about teaching experimental coherent atomic spectroscopy and gold atoms. And so basically, so first, of course, will be given by Professor Bimolendu Dev. So which will be on the main theme and the purpose of the discussion, which will say.
And the purpose of this panel discussion, so as you see that the present graduate teaching and teaching methodology in quantum science require substantial modification in order to make the science graduates sufficiently eligible to work in the emerging quantum science and quantum technology. So as you know that quantum science and quantum technology are based on basically 4 pillars. These are quantum sensing and metrology, quantum computing, quantum simulation, quantum communications. So underlying working principles of these 4 areas are primarily based on the fundamentals of new quantum science developed over the last 5 decades. So if we start from Bell's seminal work in 1964, so 60 years have passed now. So then many developments took place during these 60 years. So then question naturally arises, how much of these is covered in the present graduate curriculum? Second question, how to and to what extent do we need to modify the curriculum? And accordingly, how to modify undergraduate curriculum? Because we are talking mainly graduate teaching program. So naturally question arises, what should be the prerequisites in order to teach the new quantum science and technology that developed mainly 70s, 80s and 90s, because we have, it is the development of quantum mechanics. So then we would like to discuss laboratory made quantum systems, and this is about quantum engineering of systems. So we have several talks this morning also. So among those laboratory made quantum systems, we have ion traps, superconducting circuit QED, we have cold atoms and Rydberg atoms, photonic systems, we have solid state system, we have topological systems, and many other systems are coming up. So how much of this should be covered in the graduate curriculum? So this is the question we'll address in our discussion. So in the graduate program, we normally call MSc or master's program. So in the traditional programs, we have 2-year MSc in physics or 2-year MSc in chemistry, or in some places we have 5-year integrated BS-MS program. These are the traditional programs. So according to new programs, so this new, what is called education policy, NEP, so recently introduced, so masters so we can introduce masters in quantum engineering, masters in quantum science and technology, masters in quantum technology. So I will present my talk within the framework of new education policy. So we'll discuss only this new, according to the new education, the 4-year undergraduate plus 1-year graduate program. Graduate means MS or MSc program. So the main purpose of the new graduate teaching curriculum is to produce prospective PhD students, because they need to work in these new and emerging areas related to quantum science and technology. So prospective PhD students must have minimum required background knowledge that on basic physics and chemistry, and some hands-on experience in experiments in the above mentioned 4 subfields of quantum science and quantum technology. So according to NEP, we have 4-year undergraduate program and 1-year graduate program. So I would focus now here graduate program in physics, but that will have some overlap with the program in chemistry as well. So in quantum mechanics and applications, if we are to introduce some basics that have been developed after the seminal work of Bell, say in 1973, we have the verification of Bell's inequality, that the violation of Bell's inequality, for which Nobel Prize was awarded, so to Closed. And then we have Bell inequality, entanglement, teleportation, quantum computing, Bell state measurements. These have been developed mainly during the 70s, 80s, and 90s. So these fall under the basic physics curriculum. So we need to introduce some of those ideas in the graduate teaching program. And then related to these fields are the coherent spectroscopy. So by coherent spectroscopy, we mean basically laser manipulation of atomic quantum states or quantum states of particles or many body systems. So including mechanical effects of light, then we have optical manipulation of atomic quantum states. Because if we think of single qubit gate operations, then we need to know how to manipulate the quantum states of a single particle. The dark state resonance and applications, laser cooling, optical tweezer, atomic interferometry. So these are the proposals I am putting forward in front of you for further discussions. And so we need to introduce also quantum optics course, including superconducting circuit QED. So that may include cavity quantum electrodynamics, coherent and squeezed states, quantum noise, elements of superconducting circuit. So these are very basic fundamentals in order to work in the quantum technology domain. So then we have to think of how to introduce these courses in 4th year or 5th year of NEP program. So the above suggested course curriculum substantially modifies existing 2-year master's curriculum in physics, as none of these topics is adequately covered in the later curriculum. This is obvious because we don't have right now in the curriculum these topics. Then question naturally arises, what are the prerequisites that should be covered in the first 3 years of undergraduate program? So that I will emphasize on this. So this 3rd year undergraduate program, so this is my proposal. You can debate on this, agree or disagree, so that we'll discuss later. So in we have quantum mechanics 1 and quantum mechanics 2. That should remain intact because that will cover the basic quantum mechanics, that the concepts for functions, operators, matrix algebra, those things, and transformations. Okay? But in quantum mechanics, in 3rd year undergraduate, probably we should introduce quantum mechanics 3. quantum mechanics and application, that should cover the standard quantum mechanics advanced course, density matrix approach, Stern-Gerlach experiment. So when we introduce density matrix, we must introduce Stern-Gerlach experiment. Stern-Gerlach experiment both using silver atoms and the original Stern-Gerlach experiment also using photon polarization state. And then we have spin. So when we introduce spin, we introduce then two-level system. And then we need to introduce block vector, block sphere, and the applications of block sphere block in NMR, because NMR is the one of the first quantum machines that has been built, invented using the first quantum revolution. Because this is NMR and many other like lasers also, they use coherence. Okay, quantum coherence is inbuilt in that. So those are, in that sense, those are also quantum machines, quantum devices. And then we have incoherent spectroscopy. We need to introduce light matter interaction density matrix or light matter interaction linear response using density matrix equation. In condensed matter course, we introduce a linear response in terms of Green's functions. But in here, we can introduce in terms of density matrix, and then susceptibility and analyticity and two-level atom dissipation and dispersion and many other things, weak coupling limit. So that may be introduced in the third year curriculum. And then also laser physics and modern optics, Einstein's rate equation, density matrix theory of laser operation, laser system polarization, elements of some elements of nonlinear optics. So a master program in quantum engineering, quantum science and technology will cover all of the above topics plus some additional topics in applications and hands-on experiment. Several foreign institutes such as University of Paris, UCLA, then other also universities in the US, MIT, Harvard, University of Auckland, ETH, Zurich have introduced such programs. Some Indian institutes such as IIT Kharagpur, I know that IIT Jodhpur, they are planning to introduce such programs on quantum science and quantum engineering. So this is the table showing at which year and semester we need to introduce these courses. So this is a proposal that in the third year, 6th semester, we can introduce this quantum mechanics 3, which is quantum mechanics and application that I discussed right now. This may be a core curriculum, and that prerequisite should be quantum mechanics 1 and quantum mechanics 2. So these will cover the development happened in 70s, 80s, and 90s. And then in the second or third year or fourth or fifth semester as a prerequisite, we should introduce atoms, molecules, and spectroscopy. So this is basic structure, concept, density matrix, absolute linear response theory. Then prerequisites will be covered in mathematical physics and maths for chemistry. So that will already covered in first 2 years. And then fifth or sixth semester, lasers and modern optics. And then from fourth year onwards, 7th or 8th semester, we can have this quantum mechanics and application 2. This should cover the developments of 70s and 80s and 90s. And this should cover some prerequisites of this density matrix as we discussed. And this should be a core with a star or elective with this symbol. That course should be master in physics with specialization in quantum science or master in physics with specialization in other subjects. For this should be an elective. And then we should introduce atomic in the fourth year, 7th or 8th semester, atomic physics and coherent spectroscopy. That should cover the 70s, the developments of 70s, 80s, and 90s. And that should be either core subject or an elective subject. And then also quantum optics and quantum information, that should be only core. For the students who will do masters in physics with specialization in quantum science or quantum engineering or quantum technology, whatever. And quantum systems and applications that, or engineering of quantum systems that I discussed. And then what are the quantum systems used for second quantum revolution in the context of second revolution? These are laboratory made systems that have multi-particle entanglement or topological properties. So this is one type of quantum systems. Another type of laboratory made systems in which multi-particle entanglement can be generated with external fields to perform quantum logic operation or other tasks for quantum science and quantum technology. Or third type of quantum system, laboratory made system, which can be employed for quantum sensing and quantum with quantum short noise limited or below quantum short noise resolution. So this red type quantum systems include superconductor, topological insulator, topological system, graphene, while semi-metal spin liquid or Dirac materials and so on. And this blue type ion trap Rydberg atoms, Bose-Einstein condensate, cold atoms, cavity QED, superconducting circuit QED system, photonic system, etc. And these green type should entangle photon sources, squeezed light sources, cold atom superconducting circuit QED. So with this, I end here. So I think is like one, and then the speaker after me, Professor Saptarshi, is two. So I'll be mostly discussing about the methodology, and he'll be mostly focusing on the content wise, because whatever we are discussing here, so the biggest stakeholders are students, and if the students are not motivated, then whatever content we make, it will not come out to be a very successful result. So I will try to focus on that, how to understand the psychology of the student and how to get them motivated so that they really feel to do something creative. So the picture what you see here, so at the very center, this is actually some graphite flakes which were levitated by a laser, which are coming from this side, and this is just a lens, and this is the this is a paper on which this laser beam is there. So you can see this is a very simple setup. This is done by some students who had just completed second semester and then started the third semester at IIT Delhi in MSc in physics. So now for this experiment, I just told them like a conductor in an orchestra, just do that. But they were attending the classes, and then so in the electronics class also we had some hands-on experiments, and then my TA is also sitting here, Deepsika. So we did really hands-on stuff when teaching electronics, because we believe that electronics is something which cannot be learned by doing pen and paper. So it was a very good exercise. And then when we gave them this task to do, of course with the help of a little help of some of my PhD students, they actually did it. It took some time for them, few months, but now they know the methods which are needed to image like a very tiny objects. And then this tiny object imaging is very similar, not that different. If you go to trapped ion quantum computing or Rydberg atom quantum computing or any other imaging thing. So, and as Professor Dev was mentioning, this laser was one of the first quantum machine. So they also know how to tune the laser, how should be its current and the temperature, so that it really emits a very coherent wave, and it's not mode hopping between two coherent states and so on and so on. So with that example, let me go to a little bit more in the outline. So I'd be mostly covering on this teaching methodology, and then few things about course content, but not telling the subjects, but what should be the segments about teaching, right? So now the way we teach nowadays, so you can correct me if I'm telling it wrong. So we assume that the brain of a student is a kind of a box, empty box, and we try to fill it with information. So we are now having a quantum sensing and metrology conference. If you think of how to store information in a medium, so we just store the information and then we judge its quality by two factors. One is the efficiency, so what is coming in the input and how much is getting absorbed or stored there. So that is the efficiency. You also check for students that how much the student is getting captured in one turn, or do I have to tell the students 5 times or 10 times. So, and then the other thing is that we take exams after certain intervals. So that means the information what is stored, whether it is staying for a long time or the student forgot it after he or she is getting out of the classroom. So it's again this information lifetime, right? So now this is a thing which is actually getting practice over very, very long times in ancient ages. And now whatever like we are having there, this is maybe with a little bit small variation, but at the end conceptually this is similar. Now what we are having now, this quantum science and technology, this is a field which is actually developing almost every day. And whatever we know by now is maybe a very tiny part of it. So that means it will continue development for, if not exponentially long time, but at least for some large finite number of times. So we should make a plan like how to train our students and of course myself to this newly developing and challenging content which we are going to learn in one hand, and then we are going to teach the new students. So that is something brings this design thinking. So they should be not seeing something is ready and then we should get some characteristics, but they should really get these things as some small components like Lego, and they should learn how to put them together to get something meaningful, which also obeys the rule of quantum mechanics. So that is something I thought would be meaningful, and then again this develop the brain to deal with new challenges. So at the moment, so I don't think that the students whom we teach, their brains are really trained to the to a newly developing environment. Let me give you one example. So this is a pyramid. Is something called Bloom's taxonomy. So when I joined IIT Delhi, then I was also quite puzzled how to teach, because before that, when I was a student, I was somehow not having a very happy feeling, and then when I joined, so then also I was in the other side, but I didn't had the this happy feeling again. So when I was teaching, so I was trying to understand, and then I talked to several of my colleagues. So then somehow I came to this point that this how you are teaching and then how the information is getting transferred. It is not only remembering and then writing, which is actually only the first part of this pyramid, but there are also a few other segments like understanding and how one is applying and how analyzing and how you evaluate. And then once you reach all these stages, then you go to something creating new. Now, how do you train and examine some student is having all these capabilities? It's not so easy actually. And I find really very strange results. So you might think that the student who is getting maximum numbers, 90 out of 100 in a class, that is the best student. But if you look into this structure, you will see that maybe this student is the best in this, but then these other things, this student is completely failed. I have seen that. So because I make these questions in some tests in this segmented way. And the student who got maximum, he or she got completely zero in the other. On the other hand, there are also students who got really nice thing in this evaluation and analysis part, but they did not get much in this. So far the questions papers what we have been setting, these are like problem based, or like if we read some theory, we have to write it. So these are mostly test of the student on this part. I am not 100% sure whether we have really explored the capability of students to this upper stage. Now, I don't want to discuss too much here, but if you want to understand this much, you have to look into the clinical psychology, and then you have to really go to this Maslow's hierarchy laws and then Adler's theorems. So if you look into those things, then you will see that anybody will be motivated to learn and do something beyond the stage when he or she feels their fulfillment is so some of their needs are completely fulfilled. So one of the main requirement is the safety. Now, what I feel is that our students, it doesn't matter it's in a physics, engineering physics or mechanical engineering. So they all try to learn data science nowadays because they feel safe to learn this, because after their BTech or MTech, they will find a job there. So I think that gap is there. So you also should think not only making a good curriculum, but like this thing of motivation, which will motivate them. Okay, if I now understood this, if I now do it in a good way, then I can apply there, so people will hire me. So until we have this safety feeling fulfilled by to the students, so I don't know how they will be motivated. And if they are not fully motivated, it will be very difficult for them to drive to this creative thing. And as we all realize that this making a quantum computer is not something written on a textbook. We know how to make like pi pulse, we know how to make Ramsey spectroscopy, but we don't know how to characterize it, this decoherence for hundreds of particles at the same time. So that needs the creativity. So now this course content, so there are certain things. So for example, the selection process. So if you look into the what is needed for quantum computing, if you look into the picture of an ion trap or a IBM quantum computer, you will at the same time see the Schrödinger's equation. That means you have to understand theory very well. And you will see that you have a superconducting qubits or atomic physics knowledge is needed, optics knowledge is needed. You need to make the machine running, so you need to have a knowledge of electronics, and you have to have a good knowledge on mechanical design and fabrication. And of course, none of this curriculum what we have here gives all these things together. Now, how to build this workforce together? So that means when we are selecting this student for this particular master's program, we should really think what should be the criteria, whether the students should come with like a gate cleared with physics, or gate cleared with computer science or mechanical engineering. Now, if we want to accommodate all of them, then we see that all of them are having certain level of gap. So that gap needs to be addressed, so that after first semester or second semester, all the students who are coming from different backgrounds, they are on the same page, right?
So that brings to this, I think, some of the elective courses here. So that they can take this elective or bridge courses, which may be taken before the core courses are taught, so that all the students from various backgrounds are on the same page, right? So already Professor Dev was mentioning many of them. Okay, now besides this, core courses, already these elective courses are needed for two. This one is this bridging the gap, and the other one is, so if someone wants to be more expert on, making the theory part, or making the neutral atom based part, or making the this superconducting based part, because it is very true that although a large number of common knowledge is required for most of the students who will be working in this field, but at some point the student has to choose a specific expertise, because one student cannot really get like best expert on like all these things. So that would be the requirement for this, some more elective courses which they can do after the core, where they would like to be more expert in the long run. And then there are two other things. So one, like very good hands-on experiment is needed, whether it's an experimental or theoretical, but it has to be fully dedicated on a R&D level, research level, so that they learn. So not like that my supervisor told me to solve this equation, but I'm doing it, but really they should find out what is the problem, and they should navigate themselves towards the problem statement, and then they should solve it. It doesn't have to be very big at the beginning, but they should know the process. That is the main motivation. And then other thing is that whatever we'll be doing here, so for the case of quantum computing and the sensing and communication, these are not at the research level. They has to come to the real world applications. Otherwise, they will not have much meaning. So now, in order to do that, these students should also know how to bring the research level thing to a final, fully polished thing, which can be working in a real challenging real world problem. So that means this decoherence and all other whatever problems can be, like if you put your quantum computer, you make it here and then you put it somewhere where a lot of vibration is happening. So how to deal with that? So all those real issues has to be considered. Now, so one question I have here, so now when we talk about this industry experience, so in India, this might be a bit challenging, but I think definitely we should think, or maybe some of these high hubs who are dealing with quantum technology, they should come up with some plan. So how to give the students from India exposure to those points? Because in Europe or in US, that's not a problem, but in India, you can really count how many companies are there. There are actually not any or many companies. So now, yeah, so that was more or less it. So now I think you will speak. Yeah, thank you.
For asking me to say a few words about graduate teaching in quantum science and technology, and also Bodhaditya for nicely setting up the tone for specifically this area. So when Professor Deb asked me to say something about it, I immediately went to lab and asked my students that what would they have liked during their master's and graduate coursework, so that they would have been more prepared for the kind of research they are doing. Just to introduce, we work in the area of cold atom, Bose-Einstein condensate, quantum sensing, etc. A subject which is not on a daily basis taught in the master's and PhD level. Dr. Sanjukta Roy, my colleague, she also helped in preparing these slides, a very few of them. So now we agree that there is a big gap between what presently an MSc and PhD coursework and actual research work. And when we ourselves started our research activities, first as PhD student, then postdoc, and now as faculty, so we thought that this is normal. But it doesn't have to be normal, that the transition from the educational background to the research can be made more streamlined. So this, correct me if I am wrong later, that this gap exists, and the gap is even more visible in experimental subject and requiring advanced technology. So this is my personal experience, and also when I asked my student, they also kind of agree. So I think This is the, for example, what are some examples, and I will only limit myself to the examples what I face, and again there will be more discussion, other areas will come up. For example, lasers and other sources of coherent electromagnetic wave, they are taught to some level, but then it comes to working in the lab, so there is a discomfort and coherence, etc. So the same idea goes with the detectors, be it photo detector, single photon detector, or some kind of correlation detector. When I mean that, so this is not very clear to the students when they are starting their research work. And then ideas of quantum correlations, specifically light matter interaction and quantum treatments, which is a common theme in various quantum development, not just in sensing but also other areas. And then the term spectroscopy, many people think is that there is a spectrum and that's the end of the spectroscopy, beginning and end. But there is a entire very fat books written on these. So then again, coming back to the words which were mentioned before, precision measurement techniques such as ultra cold atom, BEC, etc. And I have not mentioned like this idea of quantum sensing. Computing, many people have some idea what it means, right? Popularized nowadays, but things which are more practically usable in near future, what I feel is this quantum sensing, quantum communication, and so on. So it's not very clear to the students. So a course what we want to build should be to bridge this gap. Okay. So now what is expected from a fresh PhD student who should have some level of understanding? And I'm not talking about whether someone is good student or not so good student, because that question doesn't come. The question is that first thing one should realize that whatever quantum mechanics 1 or 2 they have learned, and the quantum technology and application, which is this QTA, National Mission on Quantum, there is a difference. The quantum technology and application is not just extension of the advanced quantum mechanics, what is typically taught in the master's level nowadays. And then some very important thing is required, specifically again in the context of experimental aspects and technology, is the instrumentation and the peripherals. For example, how the instruments behave, how the instrument work, not just as a black box, and also how to interface the instruments and what is being read in the instrument, and how to actually analyze this data. And many excellent lectures over the past 2 days about quantum measurement happened, but some of these ideas should get into the teaching as well. For example, what is meant by quantum measurement, ideas like sensitivity, accuracy. So this is not even before quantum, like a colleague was telling me yesterday, even a statistical analysis of the measurement about sensitivity, bandwidth, and accuracy. So these ideas needs to be clear. Means they should be even in the classroom teaching. It's not very difficult to do. And then I will come to this, some hands-on training on relevant experiment, internship experience. This is required. Professor Bodhaditya also said about possibility of even collaborating with industry in that cases during coursework as well, and also advanced laboratory. So training on experimental data handling, analysis, and focus on the experiments with quantum systems. So these kind of things are required to be. So again, I will be focusing on this coherent atomic spectroscopy and cold atom. So some of the topics I have listed, which is required eventually, since we will all together make a white paper. So things like when one talks about ion traps or atoms in a trap and using them as quantum objects. So atomic structure, and specifically atoms which are very, very useful for this kind of measurement, like alkali and multi-electron atoms, and spin orbit coupling, interaction with static field. So they need to be taught at some level. Then atom light interaction, there are idea like Bloch sphere, Rabi oscillation, optical Bloch equation. These things also should get into a subject. I don't know at which semester, but somewhere before they start this. Precision atomic spectroscopy means some of these points I have put: fluorescence absorption, Raman spectroscopy, saturation spectroscopy. They should be taught. Again, coherent excitations like pi pulses, pi/2 pulses, atom interferometry, Raman adiabatic passage. So these are the topics which are really interesting. Some modern technological tools like optical frequency comb, it's not very difficult to grasp at the level of masters or graduate school, and ideas like electromagnetically induced transparency and other coherent manipulation, population manipulation techniques, they needs to be taught at some level. Continued, something very important, as Professor Bimalendu says, that lasers changed the game here nearly 60 years ago, and they need to be taught at some detailed level. Then neutral atoms and ion traps, various geometries, and optical and magnetic trap for atoms, laser cooling and trapping of atoms, Bose-Einstein condensate and Fermi-degenerate gases are some specialized topics which almost everyone is aware of, but they need to be taught in one lecture at least. And then what I am coming at, this precision measurements. For these, there are modern tools like which is known as Rydberg atoms, and then sensing of different electric, magnetic, radio frequency field, etc. Then quantum computation and information processing using cold atom. And then I have listed various instruments which we use on a daily basis, and students, even the best of them, have seen for the first time when they come to the lab. And this needs to change at some level, and like CCD cameras, spectrum analyzers, etc. So now I just wanted to say a few words about some possibility of hands-on training. So I am aware that not every place expensive models and demonstration can be done, but for example, this can be done in a three-phase approach. The first are some low-cost examples. There are some electronic circuit analog of electromagnetic induced transparency. Just example. There are many such things, quantum phenomena for teaching purposes, demonstration. There are something which doesn't cost anything practically. Every university can afford them or ask the student to get into that. And then very simple demonstration of ion traps, not the level at which you use them for clocks. I will show you a picture later. Many of us actually make them for fun. And then demonstration of something like Raman effect using even laser pointer and spectroscopy, just looking at the Raman scattered light from water. So just example, many can be added. For example, this is something I was doing a few months ago for demonstration. You can simply send green laser and some simple red filter will show you that some small amount of Raman scattered light can actually be seen, and this is something very instructive. You don't need very expensive devices. For example, using very simple kind of electrode and applying oscillating electric field with some transformers, you can trap some charged particles and actually see some stability diagram of the trap, and this can be set up in the laboratory in of the order of few minutes, and it costs nothing, right? And so these even students can be asked, like Bodhaditya also said, that a nice demonstration of scattering from tiny particles. So these are really instructive, because then students will be more engaged, and we will also be feeling some level of satisfaction that the teaching is really giving an immediate result. So then there are moderate costs. Okay, this upper limit can be extended for the kind of things I have said. For example, simple saturation spectroscopy, you don't need an extremely expensive laser, but they can be set up at the cost of between 3 to 8 lakh. I estimated that if some of the components are also home built. And of course, laser cooling and trapping for simple demonstration will cost a bit more, but not orders of magnitude. It can be demonstrated, and many universities, institutes now have such demo units, right? And some simple measurements can be done. Single photon sources, non-classical states of light using something known as Q plates, phase plates, etc. They can also be developed. So that is another few examples people can really help. For example, these are the very simple setups for a saturation spectroscopy and some very simple laser cooling setup, etc. So of course, real life lab looks much more complicated. Just I couldn't resist showing a picture from my lab. But anyway, so what I mean is that there are another aspect of hands-on teaching or training, that is exposure to the research facilities and also to industry. And that, of course, not every institute and university can expend for each student, but then some travel and hospitality students can be encouraged to go to different laboratories, and I am sure that not just me, many other faculty members will encourage for short-term visits, interaction, and so on. So with this, I would like to say that I am looking forward for everyone's comments later on. So
from IACS Kolkata. Quantum information and
Yeah, thank you, Vivelinda. So I'll do something different. So I have been teaching a course on quantum information and quantum computation for the since so the first time I taught was in the spring semester of 2009, and this was primarily for our 5-year integrated masters or BSMS students, and this would be the second semester of 4th year. So they would have, so the prerequisite that would be required was basically all the courses on quantum mechanics, solid state physics, statistical mechanics, because I assume a little bit of density matrix is introduced to them. So these are the basic courses that are needed. And of course, we have the basic electrodynamics and all the courses. So, so Professor Panigay had told me to also talk about something that we had developed a course on quantum information and computation. This was an initiative by MHRD. They had asked us, and it was basically modeled in the lines of Wikipedia page, and it was primarily targeted for engineers and mostly electrical engineers, computer engineers, and mechanical engineers who want to shift into this area. Number one. Number two, also for instructors who were teaching in engineering colleges. So we had so I'll just scroll down and show you these things. So this is, so basically in the course materials, there were primarily 3 important components. One was the book chapters, so course materials. The second was exercises, and there were some presentations which were made for the students, beg your pardon, for the instructors. So how they will take the class. So that was also given. So basically everything was tailor-made for them. And I should also acknowledge a number of undergraduate students who have helped type these courses over a period of time. So, so this was the format of the course. Okay, so it's called ICT Wiki and quantum computation and introduction. And it was online, but now, so it was hosted from a server from IIT Kanpur, but now it has been taken out. So I'll just tell like this was, I think it is a bit too expanded. So let me just reduce a bit. Yeah. So, so topics. So this were the top. So this was the first chapter, basic quantum mechanics. Okay. So I'll also show you some of the chapters. So, so basically introduction to vector space and Hilbert space, because so this was for engineers, as you know, so they are not introduced to such things, linear operators, all the things that were there, and various lectures were given, and that were also typed up into PowerPoint presentation. Then we had introduced qubits. For that, of course, we introduced polyspin matrices, and then what are quantum gates, etc., etc. And then after introducing qubits, we also went what are composite system, in the sense more than bipartite system, like more than one qubit. How do you realize them? That kind of thing. And of course, problems and discussions. For every chapters, there are number of exercises and problems. And then we titled it Magic of Entanglement. So in that we introduced Bell states, EPR paradox, and of course, since they are not, engineers are not familiar with density matrix, so we had introduced density matrix. I'll just show this lecture probably. And then identifying and measuring entanglement. So basically the both for pure states and mixed states. So and then some application of quantum protocols, so teleportation. So here we did a detailed all the BB84 protocol was there, but also like how it can be done using Bell states and non-maximally entangled Bell states also. Then using 3 qubit states. So mostly, so this was basically again a little bit of application oriented, and then problems and discussions. Then was super dense coating and quantum information splitting. In that we also, and then we also had a quantum algorithm. So we gave basically Deutsch-Josa algorithm, then Grover's algorithm, and also Shor's algorithm. And we also gave a bit of like how to do Shor's algorithm using NMR. So that was a Chuang and Gershenfeld's paper in Science in the year 1997. And then non-destructive discrimination. Now these are optional chapters. So depending on the progress that the students made, whether this will be covered or not, this is less. Okay. So this was, as I said, that Shor's algorithm, implementation of Shor's algorithm using NMR quantum computation. Now in the beginning, you know, the NMR was the first technique for doing quantum computation. Now, of course, there are a lot of things. So so we did overview of what is nuclear magnetic resonance, introduced that, how to enact quantum gates, etc. So that, then quantum state tomography and problems and discussions. Then, so this was something which we gave because I have been working on that. So it's a bit cheating. So entanglement in spin systems. So because I come from that background, so we did give entanglement spin system. Now this is also optional, but the way we wrote down, everything was broken up, so they could understand everything. And then entangled rings. So so this is like just instead of chain you have rings. So there was a paper by Wouters, so that we did. And finally a few quantum communication protocols which were not so this was mostly in PowerPoint. And then decoherence, a little bit of decoherence was there. So basic models of decoherence, and it was, as I said, it was a project funded by MHRD and hosted by IIT Kanpur. So this was the first part of it. So I will, since I have to get out of the presentation, so I don't want to go out of the presentation yet, because there are people who are attending online. So I'll show some of those chapters later. And so then I come to the second part of the talk, where what I had taught at IISER Kolkata for a number of years now. Though the first course was taken year 2009, but I have not been continuously teaching since 2009. There were Professor Panigai and Anand Dasgupta had taught in between. So let me first introduce the curriculum. So this was taken from our academic portal, and this is actually open. You go to IISER Kolkata website, you can actually see all the course contents there. So quantum information processing. So since I'm teaching in the spring semester of 2024 also, that's why instructor, my name is there. So basically we assume that the neo intermediate quantum mechanics, which is basically Sakurai level of quantum mechanics, modern quantum mechanics, statistical mechanics of the level of let's say Huang or Patria, and condensed matter physics of the level of Kittel. And of course, in order to do these courses, they have taken other courses which are prerequisites of those courses. So again, as I said, that this was primarily for our BSMS students. So they are already familiar with most of the basic physics. So Again, church theory hypothesis is introduced, quantum cryptography. So yeah, so here tensor product states, of course there are no tensor product state, but we again mentioned that it should be there, and quantum cryptography BV. So these are the outlines, but it is not necessarily necessary that the instructor has to stick to the outline. So they can actually gear up the course according to their wish, but broadly sticking to this. And entanglement, Bell's inequality, etc., etc. So and then quantum algorithms and quantum computation, quantum no cloning, Deutsch-Jota, then quantum Fourier transform, all these things. Then of course there is a section on decoherence, and finally realization of quantum computers. Again, here also we give emphasis a little bit to NMR because that's the first. And generally what I do, depending on the number of students, like if it is 15 or less, I give a term paper in which to somebody I give superconducting qubits, to someone I give cold atoms, like that I just distribute. And but if it is more than 15, because I have to sit for 15 presentation, if it is more than that, I generally take a end semester exam. I don't give term papers, but then I ask them to read. So the textbook here is given is Nielsen and Chuang, but I also use Preskill. Okay, Preskill's lecture notes. And then I have the course contents, but let me just go out of this and show the other thing. No, this is not this one. Okay. So these are the lecture notes.
Much time. So let me just quickly tell that we have been teaching experimental optics lab, myself and my colleague Professor Banerjee, IACS Kolkata, for many years. And we of course will share our experience during the discussion, so I will not go there for much details. So in most of the cases, what you see that you see in most of the Indian universities and institutes, the optics experiments are typically what we do is this kind of experiments, which is purely classical optics experiment, very traditional experiments dealing with the wave nature of light, interference, diffraction, sometimes the vectorial nature, polarization, Malus law, at the most Michelson interferometer, talking about coherence. So all about the classical domain. And unfortunately, there is really nothing we learned. So if you go to a class of physics students, you'll see that most of the people are interested in quantum mechanics. And you ask, I think that most of the students will talk about quantum mechanics, what they learn, the philosophy, etc. But unfortunately, light, which actually can be used to demonstrate a lot of quantum philosophy, to see it, no such experiments really exist, at least in our countries, in various institutes, including the IITs, ICERs, and many other places. Some of the universities are looking at, of course, these days, with that surge of the second quantum revolution, a lot of new experiments are being set up in the teaching lab, experiments with single photons. So I have made a collection of those. I'll just quickly go through, and then of course we'll discuss. In our this optics labs at IACS Kolkata, we have, of course, as I said, that there are certain advanced level of experiments that we have been trying to set up in our lab, mostly based on, again, in classical optics. So for example, we in our lab, we have developed something dealing with geometrical phase of light. In the morning, I was talking about geometrical phase, the two variant of the geometrical phase. So both variant you could show in laboratory by a fiber, twisted fiber or anisotropy medium, setting up a Michelson interferometer to see the phase, because phase you can talk about, you can see it in an interference. So those kind of things we have done using spatial light modulator to generate angular momentum states of light. So these are, but not, you cannot say these are per se any quantum kind of experiments. So, but one of the problem that we see, of course, is that the complexities, most of the time you see experimental complexities, knowledge about the detectors, which is very important in setting up any quantum optics experiment, possibly is lacking at the undergraduate and the postgraduate level. And even say, for example, when you talk about undergraduate or postgraduate experimental teaching, nobody is exposed to proper detectors like CCDs, APDs, avalanche photodiodes, and single photon counters. So those are something which possibly somehow we have to make them knowledgeable about this. and then think about some experiments. So another problem is of course budget. As I was telling, most of these experiments nowadays you can develop experiments in your lab with reasonably low cost, classical optics experiments, and there are also commercial versions available, which is in typically low cost within a lakh or so. Whereas if you really want to do a single photon experiment, it will cost much higher. That is one of the, I think, bottleneck. But we have to discuss whether that is what's spending, or is there a cheaper alternative for that. So I have made a list of experiments. I thought that particularly looking at the quantum nature of light. So all we talk about the wave nature of light, geometrical phase, many things, let's say, we are taking into the teaching curriculum, etc. In the morning, I was also talking about weak measurement, which is again a quantum mechanical measurement philosophy, but again can be shown using simple classical optics. But there are these lists of experiments that I was thinking that possibly can be managed. So of course, if we could just SPDC nowadays, of course, for every quantum sources of light, entangled photon, this is one that we use. So possibly it is some of the academic curriculum abroad. I was saying that they have been including this into the curriculum. So this SPDC thing, where you have type 1 and type 2 kind of two photon generation entangled photons with requisite basic knowledge in nonlinear optics, polarization, quantum optics, entanglement. Little bit of course, you have to cover, as Vimalendra was talking about the theory part. Laser, as Saptarshi was pointed out, that actually at ISR Kolkata, myself and Nayan have been trying to teach even atomic physics and laser a little bit. So that background will be needed for us for this kind of experiments. And generation of entangled photon pairs and coincident count measurements. So this is something which can be set up. If you have the SPDC setup, then you can teach how to do coincidence count measurements and do all kind of experiments. Again, you need to have basic knowledge of handling optical, electronic components, fluorescent optics, crystals, photodetector, photon counting, how it works. So a little bit of, so we at ISA Kolkata, we do a pre-lab and lab. In the pre-lab, we teach about the basics of both the theoretical background and the experimental part. And then we have the true lab. So in that modality, so this is another experiment which can be set up existence of a single photon, that a photon cannot be split, so that you make this kind of measurement. In principle, it is possible. So I've taken it from, of course, the famous paper by Aspe, which was shown in 1986, this particular experiment, which can now be set up in a laboratory to show the photon nature of light in principle. And then in experiments with entangled photons, the polarization, as I was saying in the morning, that gives you a handle to do a lot of projective measurements. So you can, just like the spin that you use in the context of electron in the Star-Neuralink experiment. So you can do all sorts of projection, basis rotations, etc. Using the polarization optics. The so-called Stokes vector measurement is one of the way to realize all the spin projections, sigma x, sigma y, sigma z. So those can be implemented in the context of single photons also, in principle. And single photon interference experiment using a simple Mach-Zehnder interferometer, which again can be set up in this context. So once you have such a setup, and of course HBT is a very interesting experiment that nowadays, of course, we always find out G2 correlation to measure the quantum nature of a single photon. So HBT experiments, the delayed choice experiment. So again, looking at the entanglement of the photon pair that you generate using SPDC. So this kind of experiment possibly. Quantum eraser experiment, a classical analog can easily be set up, of course, that if you put two orthogonally polarized light and then you look at the interference, it vanishes. As you project it to a common state, then it reappears. So the which path information you basically give that, the interference vanishes. So this can be also done in the single photon level. And testing of Bell's inequality using this kind of SPDC setup can be done. Congrumental interference, another very fundamental testing, which I think that in principle can be set up to find out G2 and quantum key distribution, etc. So these are, I just quickly looked at it and thought that this is a simple, in a very basic level of experiments that in principle can be set up to look at the quantum nature of light. And because this is very much related to the foundation of quantum mechanics, weak measurements, geometrical phase of light, etc., some of which we have set up in our lab, but I think, and also the angular momentum of light, even for a single photon, for example, so looking at the uncertainty relations between angle and angular momentum, etc. So these are just some random thoughts possibly, but I think that this is the time to actually, when we talk about optics experiment, we always talk about the diffraction, interference, polarization, etc. But we never really we have never experienced this actually, a single photon experiment in a teaching lab. So I think this is high time that we should drive towards this. Maybe funding is needed, of course, and so, but we were discussing on the other day with Professor Dev that maybe it is difficult always. For example, I was saying that if you have to have a SPDC setup and set up a few such experiments that I know listed, it will cost, let's say, 30 to 40 lakhs for, let's say, it can be shared, of course. One SPDC setup can be shared for setting up a 2C experiments, but the overall budget is high. But because quantum mission is giving so much of money for research, I think something is needed to be seen in the context of teaching also. So with that, I stop and open it for discussion.
Now, the discussion is open for comment. By participants,
why they are seeing a signal, and then they let them come. They appreciate the theory, I think, better that way.
Okay,
And then
I understood your point, but see, let me tell you a little bit about it. So, of course, it's a good idea that so the point is that the experimental part has to be emphasized more, but not, of course, at the expense of theory, right? Because creativity does not only come in experiments. So, suppose an undergraduate student, if he does not know the basics of quantum mechanics, what will he test in the laboratory? So that is, of course, very important that you learn the theory. And as a physicist, of course, we think that so quantum mechanics kind of attracts many of us because of its theory, of course, right? At the same time, one should try to see what we say in quantum mechanics. For example, we say, as I was saying, that a single photon, right? That how do you detect it? So it is a good idea to have some of those experiments in the undergraduate level. And because here we are discussing about the quantum part only, so that is what we are discussing, that in our regular curriculum, of course, there are a lot of other experiments. Now, this is another point, that whether those are just commercial black boxes, so that irrespective of whether that is a quantum experiment or a classical experiment, so that is a big problem, of course, right? That many of the even bigger institutes, they go for buying black boxes and the student just switch on the knob and take such reading. So that, I think, has to be consciously addressed. Like, so it's like hands-on building up kind of thing. But as I said, that this is, I mean, in general problem, it's not about just that, but in the context of what we are discussing here, is that we really lack even the experimental basics for tackling the quantum problems that we are now addressing. So that is to be more specific on that. But your opinion is, of course, well taken, that the laboratory has to be made more interactive and, of course, more hands-on rather than based on, see, for example, those experiments what I was suggesting, these are not like a plug and play device, right? You have to align yourself, you have to generate a entangled photon and check it, detect it, and at the same time you learn about the detectors by hands-on doing experiments, by doing, let's say, single photon counting experiments or correlation measurement, etc. So this is part of that. It is not that only going to the lab will solve the problem. That is also not true, in my opinion.
We have done it, you know that. So this is very important. That is the upside, it is inverse process. So I also agree to that. But with that background, they must have little bit of knowledge on quantum science and.
Yeah, so that is very important, that of course those experiments has to be set up. So that is what we are discussing, that even at the undergraduate level. But of course, yeah. So yeah, Professor said.
Yeah. Yeah. So I'm speaking from the perspective of a typical undergraduate college, okay, where we have very minimal, modest facility. Okay. So this is actually I am just showing you just syllabus that then you can understand, but it is according to NEP, which was just implemented from last semester. Okay. So here, as usual, you will find different subject. Particularly, I would like to, it is a 4-year right from this year. Particularly, I would like to inform you 2 points. That is, you just look at the 7th and 8th semesters. So at 8th semesters, there is several subject is there, but what is think that the instead of these 4 subjects, as you find here, instead of 4 subject, you can adopt research methodology and as a regular paper and undergraduate project focused on any specific subject area. So this may be any theory paper, or it may be on quantum computers or quantum information science or quantum technology, whatever may be the area. The whole exercise which you are doing, that it reminds me around one decade back, that there was a initiative called Nano Initiative by Ministry of Science and Technology. So they have asked all the undergraduate colleges, actually they have instructed UGC to introduce one chapter in all undergraduate colleges to introduce something new on nano technology or nano something, nanoscience or sorts of this. And then they have introduced around several units. And if you have any specific plan, particularly for the theory, then on through via UGC, if you want to bring it to the level of traditional colleges of UGC, then it may be done by percolating it through UGC to every university, then to colleges. This is number 1. And number 2, regarding there is a number of proposals, and I have attended some courses. It was developed by, I think, most probably RRI, Professor Srinivasan in Indian Academy of Sciences. He has developed a series of experiment which is very cheap, comparatively very cheap. And in his laboratory, that is in the office of Indian Academy of Sciences, he has developed these things at very low cost. And he tried to post it, then he marketed it and pushed it in various university also in institutes. What I suggest, if you are really interested to teach various courses, not only courses from the practical instruments, developments, etc., particularly, then in a central facility in say in IACS or ISAR, Kolkata or Essenburg Center, whatever may be, you should develop a teaching learning process lab where you will you can develop some inexpensive devices for laser lab. And if you have this, if you have can develop these laser labs particularly for this, then all the teachers or students, you can give them the opportunity to visit this, and if you can develop all these devices, you can also market it, so that with modest budget, all the colleges, they can purchase it. So this is my submission actually.
Okay, thank you for your suggestion. So yeah, it's a good suggestion, but of course this discussion is mostly concerned on developing a course towards quantum science and technology. So of course there are many experiments one can develop, cheaper experiments, which is a good suggestion, but probably we have to focus here mostly on the corresponding experiments in the domain of quantum science and quantum technology, which are related to quantum science and quantum technology. And one bottleneck, as we were discussing, is that to do in the context of experiments in quantum science and technology is a little expensive compared to typical classical experiments. So that is, of course, there are many classical experiments which can be developed with a relatively cheaper price. Similar things can also be done for quantum, but it is an order of magnitude higher. So that is one of the problems I think that we face. So that is one of the problems, that in our academic curriculum we really do not have experiments related to maybe let's say quantum optics or something like that. So where you can develop relatively cheaper experiments for other things like many things, of course, are done nowadays, and you can be commercialized also. The corresponding part in the quantum is a little non-trivial, so that is the main challenge that one has to address. I
May I
guess.
say something, Nivaldo? May I say something?
Yes, sure, Professor Atupta, you may please.
Yeah, actually, there are 2 points I want to highlight. I've been teaching for maybe several decades in India. I know the main ailment. Main ailment is that people, when they come for optics specialization or something, they don't have any kind of formal training or basic optics. Their idea of optics is lenses and prisms. Okay, that's what they think of. Okay, and if you tell them there is much more exciting things even in classical optics, it is hard to convince them. That is one. Basic training in undergrad optics is not there. Not even a single place in India or any course in India where they generally give optics at the level of Born or at least at the level of this other more popular book is your undergraduate book. Okay, so that is one point. Second point is that in India we start with this counterposing theory and experiment. Okay, whether this should be given preference or that other thing should be given preference. And this fight among the theoreticians and experimentalists kills our science. That is another my personal opinion. You may differ from that, but it's my personal opinion. This happens. So experimentalists think they are being underestimated, or the theoreticians sometimes believe that they are being underestimated. Till there is a kind of complete exposure to both. See, I've seen in Europe, in many other countries, in US also, the training is as a physicist. They learn both theory and experiment. A theoretician is a very good experimentalist. A good experimentalist is also a very good theoretician. Most of the labs are like that. Most of the big scientists are like that. In India, we don't have even a single, very few examples of that. That when people are proficient in experiment, they can do good theory and vice versa. And that's because either we try to give preference to one or the other. Okay, now this is under these 2 main problems understood. My suggestion is that whatever you are saying or doing is excellent kind of program. I have full support for that. What Vivekananda has shown, Saptarishi was showing how to introduce these notions. People are not familiar with experimental units or something. They see for the first time when they come to the lab. There's a big gap between the teaching level and the research level. That gap has to be bridged. And when you're bridging the gap, you need to forget that you need to be a complete physicist. That's the way the bridge has to be gapped. Saying so, I must also stress that this kind of thing, quantum initiative, is very good. The point is that, see, sometimes I may lead the student to the lab to expose him to equipments and play him around with these things. That many of the experimentalists think that way. Let him play around, he will come out with new ideas or something. But sometimes they may observe something. If they don't have the proper theoretical understanding, they won't be understanding what they are seeing. They won't be understanding what they're looking at, how to explain that thing. And that's where they have to go and seek the help of a theoretician. That kind of thing should not be there. Had he had the proper theoretical background or something, this kind of requirement would not be there. So my suggestion is that design a course which has got both theory and experimental kind of exposure. Students are exposed to this thing, and this project thing is in a sense killing the future of our science. I've seen in IACS, in other places, second year onwards, students are keen in doing projects. What is the target? Target is they want to have a gateway to some foreign labs or foreign countries, some connections or something. That is what they do. They are now more interested in doing this kind of project and establishing contacts rather than doing science. So project part, educate them on the basic things, basic handling equipments, let's say detectors, lasers. They get them the way I was trained. The day laser was brought in the lab, it is first day it is opened. And then we were asked to assemble the laser system. The power supply would detach everything, then you just gather them together and make it work. So here we can't afford to do that because we don't have that kind of resources. And the other thing is that from classical to quantum is a big jump, as Nirmal was mentioning a number of times. SPDC, for example, SPDC you want to understand. If you don't have ideas about nonlinear optics, don't understand nonlinear optics, down conversion process, you can never understand this SPDC. 1987, Mandel did the experiment in 1987. on this SPDC heralded single photons or something. It took us several decades to do first such experiment in India. Why? All these things we know, all these things, all the equipment we know how to do that. But it took us so much time to just replicate this. Now the quantum initiative had started. We got money. Many places like this IIT Jodhpur, they got the money just very first thing they are doing. They are setting up a SPDC lab, and they want to make it part of the teaching kind of program there. So these are the kind of initiatives. If the government is putting in money, spend a major chunk of that for teaching purposes and setting up these lab facilities, be it very costly or not that costly. Set up this thing where the world has gone much beyond. We are lagging behind. We need to at least catch up with them. And the idea is not that theoretician gives the idea and the experimentalist's job is to prove it in the lab. Experiments go much beyond that. Doing the experiment, they can get some new effects. Then the theoreticians have to struggle how to explain that effect. That's how theory and experiment complement each other. We need to understand that. So I think that's about all what I wanted to say. And this kind of, if we learn how to work in jointly together, one of my colleagues says we don't know how to collaborate. So if we learn to collaborate, we learn from each other, then things will improve. And this do require some basic undergrad level optics course, non-linear optics course, this optical resonance course kind of thing, which we started a long time back when Girish Agarwal was here in India. We had this kind of thing, and people used to say we used to offer a very nice course on this quantum optics and non-linear optics and everything. So now those things are gone. Not even a single place has this kind of full-fledged kind of courses. Not even a single educational institute is there. And basic optics, just forget about that. Optics and spectroscopy, basic optics and spectroscopy, not even a single place offers that kind of thing. I think once we mend those things will improve.
So I just wanted to give responses of the question what you have been asking and you have been asking. So my first slide, what you saw, that was actually built by two master students, and I have not touched them at all. But now the question is, in the MSc, we have about 65 students. And if you look into the first year BTech, then it's more than 600. So what you was taken is very, very valid, and I also tried. But now how to facilitate students to that large scale, that I think we have to think and come to a solution. That is one point I want to make. And I think what you were saying, that is very, very valid. Actually, I was also timetable in charge for the physics department for 3 years, and I felt the real issue on the ground. So we really want to give the basic courses and give the opportunity to the students to learn from these courses, which will give them the real life idea. Now the question is a little bit complex. Not only it's a problem of the students or which courses we can teach, but also the expertise which is available in the department and in the institute. So we really find it difficult to find teachers who can really teach those courses. So maybe there also we need some kind of a little bit longer or midterm planning, that if we do not have those type of skills to teach the students now, how can we bridge this gap in next 5 years or 10 years, so that we make a plan, so that the example what you have been giving, so those kind of faculty members join more in the institutes who can maybe facilitate students in a more better way. That's all I wanted to say. Thank you.
Today for discussing this thing about so all these things have to be
So we have to
be
note all this
discussed, and for your new curriculum you have to introduce, because in your experiment what we have shown, we get the material, we get the laser source and get the output. So it's a kind of just the principle one can understand, but not they are making by hand the materials part at the same time the laser part. If they build the laser and see the inside and make the materials and see how to make the materials, then the thing would be more interesting for the students.
So there's one so another thing is that these students are overtaxed with the course curriculum.
No,
So,
I agree. Because we are discussing today for the new
so actually
curriculum. So
even give them the opportunity so they can actually work full time.
because your point is correct. If you have 600 students, 100 students is a problem. But while devising a course, you have to think of for the future technologies, quantum technologies, quantum. So this is very specialized thing.
so
So
advanced
how to
experiment.
approach is really difficult issue. You are correct. You are correct.
So advanced
Right.
experiment. So just one second.
I want to mention that what you also told, that experiment should be experiment and theory should go hand in hand, and for that, as Shaptoshi told, I don't know what it, I told this Shaptoshi. Shaptoshi told that he showed that different type of experiments is being developed, and to when one will introduce the theoretical course, quantum optics, and one will have a clear-cut idea what type of experiment can be introduced with that course. And for funding is a problem, but that also one have to check out that how this funding can be obtained. So it is very necessary to attract the students and also to teach them, I mean, to give them the at least their understanding. It is very necessary to do experiment and theory side by side.
So I just want to add something, what Professor Dev had presented. So what Professor Dev was saying, that it was in addition to just a few courses in the standard master's program, NEP also wants us to design courses like MTech in quantum technology, like IIT Jodhpur is coming up with that. Then Indian Space Technology Trivandrum already has a MTech in master's technology, and we are also going to do so. That's actually they want us to develop master's courses, MTech courses, or MS courses in quantum technology, because if quantum technology comes, they want so primarily geared for engineers also. So BTech in electrical engineering or electronics and communication. So they can come here and learn those techniques, because they're not taught quantum physics or experiments in quantum physics, so that they can go and participate in the industry which is going to come in future on quantum technology. So that is another aspect of it. So.
Can I make a comment?
Yeah. Yes, Professor Krishnamurthy.
Well, this is actually a wonderful initiative and extremely important, given the fact that, you know, we as a country had missed the silicon revolution, the electronic chip revolution, and we are trying to catch up on that. I think it's extremely important that we don't miss the quantum technology revolution, and for that it's extremely important we do educate and give practical training to our students on this. So I mean, a couple of points about what Professor Nirmalya Ghosh and Professor Dattagupta had spoken about. So, I mean, things like SPDC are actually extremely important experiments to be taught to the students, to give them a sort of practical feel of how to experience single photons. And given the fact that, yes, they are expensive, so we may only be able to get maybe one or two setups in hand, for example, a few setups in hand. But possibly one way to do this is to, you know, during the entire course, to have a combination of experiments that address both classical optics and then towards the end quantum optics. So classical optics experiments could give the students a flavor of how to do basic alignment of optics and all that, which as Professor Dattagupta rightly pointed out, students lack. And then once they are, you know, once they have a very good feel of how to handle optics properly, how to do basic alignments and things like that, quantum experiments then can come in maybe towards the end of the course. So even if there aren't that many setups, the students can be divided into multiple batches and at least give them a flavor of how the quantum single photon experiments work. So, but yeah, this may be a way to go. And of course, we probably have to raise some good funding, but with the impetus on quantum initiative and all that, it could be possible. So, yeah, thank you.
Thank you, Professor Krishnamurthy, for your comments. It's very helpful. So, anybody? Yes, Vishwajit. Vishwajit is from Calcutta University. He is teaching optics and atomic physics. Yeah. Okay.
We have covered almost all the topics you have discussed in your past lectures. Hello. So, and also in the second, we have laser physics and the quantum optics. We also cover all these from Doppler cooling to BEC, everything, and also EIT, CPT, everything. We have seen the students, they are very easily grasp these topics. They have no lack in the talent interview. But what the Professor Chaudhary said is the main thing. When I ask them to go to the laboratory, they lack their energy. They are not much interested. Because we don't have any undergraduate, we get the students from the undergraduate and to the college. And so I think we have to catch the student from the very early if we want to build up such a sophisticated setup. And it's a reality now. Quantum science and technology, we cannot avoid it. We have to go lateral sooner in this science. Okay. So it is possible, if it's possible, we can build up a course after class 12 or 12 standard. And then for the first 3 to 4 years, they can go physics, chemistry, maths as usual. And the last 2 years, if we can take a multidisciplinary, as also the NEP emphasis there, you will build a multidisciplinary subjects. And we can take the personals from different fields, chemistry, physics, maths, and so on. And also, I would like more emphasis that recently organized 2 lectures for our students. One from the TCS personals, they have a lab, TCS Research and Innovations, and the IBM computers. And students are much interested in hearing their lectures. They mainly emphasize the quantum computations and the quantum computers. Okay, so these things, if we want to prioritize, we have to make a multidisciplinary, and we have to catch the students from the very early, not in the PG students, we cannot motivate them in a specific fields. So this is my suggestions in concrete. Okay.
I think it's a very good suggestion. And I am happy to note that your course curriculum is quite rationalized within the framework of quantum science and quantum optics also mainly, and atomic physics. So, any
I am from Aliyah University. Since the discussion is based on the graduate course, so in the before NEP, we have introduced in our university, in particularly in physics department, the CBCS syllabus, choice-based credit system syllabus. In that curriculum, in the last year, there was a discipline-specific course that is little bit advanced or special type of papers. We have given one paper that is called the photonics. And in that photonics, we have provided lasers in details up to the applications and different type of laser systems like a solid state, gas type of lasers, dye lasers, and so many, almost everything is covered, but little bit semi-classical approach, not the quantum approach purely. And after that, we have introduced holography and the fiber optics communications using lasers. And then the most important things we have introduced, that is the nonlinear optics part, which is actually most of the university colleges, they have not introduced this part where the nonlinearity can produced by the laser fields after discovery of lasers. And in that curriculum, we have taken few another part that is like a electro-optic effects, acousto-optic effects, or photon optics, like that part. So these type of parts we can adopt theoretically or in theoretical curriculum easily. But my point is, if you now in respect of NEP, if we want to introduce these type of topics or which I have seen in these few lectures, it is very easy to adopt theoretically, but the problem is to set up the experiment in university or college levels, particularly in UG level. I think 95% of the UG students come from the college overall in India. Few institutions now introduce like IJAR or like that, they are the undergraduate courses is introduced. But 80 to 90% students come from the college. And most of the colleges, they don't have a optics lab like a proper facilities. In our lab, we have purchased few sophisticated optics instrument from India and few from abroad. At the time of COVID, since the lab was totally closed, so due to lack of air condition and others thing, most of the optics products is damaged. So we have no fund to operate now that type of instruments. So for quantum technology, quantum based science, if you want to introduce in our laboratory, I think the minimum facility that to build up a laboratory having some humidifier, dehumidifier, or some air condition or proper facilities, we have to introduce by this type of mission. Otherwise, if you introduce the laboratory in a normal room, all the products will be immediately damaged, and you cannot continue the experiment for a long term. So this should be very much, in our case, we are facing lots of problem like this type of issues, because we are not able to introduce so much things due to this type of lack of facilities for the quantum based some experiments. Because Dr. Saptoshi told that spectroscopy type of palm probe spectroscopy type of experiment is very easily can develop in a laboratory, but that type of laser and optics can be should take care very carefully. Otherwise, the
travel and hospitality for students coming from a reasonably nearby area. India is big, so it also has its advantages and disadvantages. So, but that's also a very good suggestion that not every institute or university should have every facility. Some centralized facility where Professor said that, even starting from the material level to prepare lasers and spectroscopy, and so that where, one of the very important point is that maintenance, like humidity control, air conditioning and all that. So that replicating it 1,000 times is difficult. So things which are easier, phase 1, that can be done everywhere. Phase 2 can be done in limited places, and that phase 3 can be some centralized places where students can actually part of their curriculum go visit, do hands-on training. But I'm very happy to see that some effort is getting means it's being given to, it's off the ground. So this is very important. Then once it goes up, there will be some little bit of difficulty. We can always try to correct it. But at this level, if we doubt too much, then it will never go out of the ground. So something needs to be done, and it's high time. So
There is a raised hand.
This is Manas.
Yes, Manos, yes, nice to see you.
Not, sorry, I cannot be there. We are in a meeting at HRI actually, which Shrikot was with me just a few minutes back. So maybe a couple of points I heard, most of these were probably raised. So one thing is for quantum technologies, as was said before, it encompasses many different things, including materials, then of course components, then devices, and then systems. So a lot of it is not physics, it's actually engineering, a large part of it. So I think there are few ways to introduce, and this is like a worldwide phenomena, which is there are courses been given in engineering which are not at all quantum but helps quantum, like device making, or it could be component making or system building. Then there are others which are more specific to quantum science, and there are others which are quantum technology related. Now, these could be either in physics or it could be in some sort of a technology which is very specific to quantum. And these could be courses, not just modules. The others are modules, right? In terms of the lab facilities for even for building a good laser, I do not completely agree that you need very sophisticated optics. In fact, some of the optics suppliers in India now are capable of giving play around to make some of the speakers there would also be able to tell this, that it's possible to do it in simple setups. And those are used currently in all the more sophisticated ones. The other part of the story is like FPGAs, the field programmable gate arrays, which forms the controls. This is purely engineering. problem. IITs and IACS would have very strong capabilities on those, which could benefit. So I think that's a kind of more holistic part from my side.
Thank you very much, Manav. Assenboard Center.
Yes, continuing from Manas's last comment, actually, this quantum communication, actually, I thought maybe this, I should tell something about this quantum mechanics teaching for quantum theory project or science and technology. So some communication items which are based on materials. So so those materials may be qubits or at the level of qubits or quantum dots actually, or Josephson junctions or those things based on, something like quantum mechanics related to quantum dots and quantum bits and model systems regarding that, and some fantastic phenomenon of atomic molecular physics like Born-Oppenheimer approximation, non-adiabatic dynamics, non-radiative transitions, conical intersections. So those things can also be understood in a model level, not at the real atomic molecular level. So to get the test of quantum technology in quantum dot molecules. And another thing is this intrinsic probabilistic character of quantum mechanics. So the stochastic approaches like these things are systematic theories of quantum theory of damping, decoherence, system path theory, and non-Markovian approaches to deal with non-local problems and quantum slow motion of trapped atoms for there also the atomic molecular physics approach and dynamics approach like nonlinear dynamics. So those the things are also important, and besides that, this quantum optics approach and experimental laser physics, those things are there to understand entanglement, correlations, interferometry, and those things besides the typical harmonic oscillator or two-state models of quantum optics. The quantum dot system should be understood through laser optics, and also the new theorems in information theory, the robust results of quantum information, like so those things can also be understood from model systems. Say, for example, observables in 2 and 3 Hilbert space, model problems in 2 and 3 Hilbert space, like in a real atomic molecular system like a row vibration or rotation vibration or electronic vibration. Those properties are already there. So those can also be understood at the quantum dot and other levels.
Yes, I agree with you. There must be a core curriculum in atoms, molecules, and spectroscopy in the undergraduate program. There should be one course and another 2 advanced one, which is I call the coherent spectroscopy, that may be introduced in the graduate program from 4th year onwards.
Yeah, this Saikat.
Yes.
Yeah, I just wanted to quickly add one point, just kind of continuing with what Shubhashish just now said. Hello.
Yes.
Yeah, so in IITs, for example, we have this very successful e-masters program, particularly aimed for people who want to have like short modular courses. I don't know if it has been already discussed here. So that is basically like short 6-month kind of courses, where actually like it turns out that a lot of industry people want to learn quantum technologies in a way where they can function. You know, they don't want to be quantum mechanists, but they want to be a functional quantum technology, like at least terminologies and so on. So they are actually those kind of e-masters courses might be very useful if you're considering, because there's a great demand for that now, because there are so many companies coming in, and those will be very short modules. Essentially, what Professor Dattagupta said, but a compact version of that for non-physicists who just want to learn the technology in a functional manner. So that might be another possibility.
Okay, so thank you very much for your comment. So I just want to say a few things related to this last few discussions. So for getting to the industry, I think it's not always enough to have the bachelor's level degree, especially when it comes to quantum technology. Because if I take some examples, so just let me take the first example of Rigetti. So I think all of us knows the name of Rigetti. This is a very good leader in quantum computing using superconducting qubits. So this is founded by Chad Rigetti. So if you look at his educational background, he was trained as a PhD student and then worked as a postdoc in IBM for a few years. Then he founded a company, and then this is a very, very successful one. Now there are a few other examples like Atomionics in Singapore, or this Alpine Quantum Technology. So which is also founded by Thomas Monge, who was a PhD postdoc and then senior scientist doing quantum computing research using ions for several years, and then he founded. So this is such a topic where this industry level skill is really required. And I think what Professor Saurabh was saying, that what we are asking here is not to change the curriculum, but to add a little bit more so that it looks little bit more packaged and polished, so that it matches with the requirement of the industry. So we are not telling that we would like to compromise our syllabus of basic and fundamental understanding, but we would like to add little bit more so that it goes out of the classroom, it goes out of the textbook. So that's all. Thanks a lot.
I have just one suggestion. I teach physics at the undergraduate level at a college which is affiliated to the University of Calcutta. Okay, so in the first class, every year I just take a survey that what topic motivated the students to choose their subject as physics. And the common answer is the astrophysics. Okay, so from the very beginning, I mean, from the school level, the students are motivated towards astrophysics. So if we want some human resources in this particular field, we have to popularize the subject. So I have a suggestion that we should conduct some outreach program every year. Okay, so at least so that we can reach at least 10% or 20% of the students who are taking admission at the UG level physics.
Okay, a good suggestion.
So this.
So this outreach program, we're having students from class 5 or 6.
Okay, actually many students from the University of Calcutta moves to higher educational institutes like IT or other institutes. Okay, so at Kolkata, I think there should be some outreach program that will help to motivate many students.
Yes, we can do so.
This is one point, and another point has already been mentioned. So I am just repeating the same. If a common lab is created, which will be accessible for the UG level students. For example, every year you provide 7 days or 10 days so that the interested students can join.
Would you like to make any comment?
There were very good suggestions all around. The only problem is, are we looking at the quantum, the numbers? Means if any institute is going to work as a higher educational institution as given by NEP for undergraduate colleges, so they have to deal with maybe 6,000 students for 7 days. Are we doing the maths? Means
yes,
we understand if nothing else we'll require some extremely dedicated teachers will maybe practically stop doing regular science and just deliver lectures on these topics. Because at undergraduate college, we do that. So we know what toll it takes to train the students in the same thing again and again and again. So, and yes, NEP does expect a lot of institutions to take up the role of higher educational institutions. So NEP does expect, so the government does expect some faculty members from those institutes to take up the responsibility of training the students from other colleges. But are we ready for the numbers? Means any experiment. Let's forget about 5, 6 and open experiments. Let's forget about open experiments. I'm just talking about one curriculum experiment. Are we ready to do that? So maybe we should start small. Start with a standard theoretical curriculum with maybe 1, 2, 3 experiments that can be spread across or shared with a lot of other colleges and institutes. Maybe that might be a way to start things.
Very good suggestion. Yes. So you can email me giving your suggestions in writing also. So we'll incorporate that in the white paper, because about policy making, policy matters, everything is not at our hand. So it requires broader discussions at the broader level, say. So this, whether government funding will come to teaching and setting up laboratories and improving the facilities at colleges, undergraduate colleges. So that maybe we can reflect that in our write-up white paper. Okay. So, but
I think one good idea would be to start. Let's say you plan to train about 100 students or something, 100 or maybe maximum 200, not more than that. Start at that level, at a small number level. Large numbers you can't handle. Okay, so start at 100, 200 level, train them such a way, and they have to be handpicked. These 100 or 200 students have to be handpicked. There should be a proper selection procedure and everything. They will be trained from this undergrad to postgrad and this final degrees and everything. They need to be trained both in theory and experiment. Different kind of curriculum for them imposed on them. Different kind of rules for them. That's the kind of thing needs to be installed. Otherwise, this kind of initiative cannot take effect.
So it is
So
now.
it cannot be large number kind of. It cannot be applicable to large number of students. 4,000, 5,000 is impossible.
Yes, I understand. Yes.
But undergrad courses can be introduced. Undergrad optics courses can be introduced at every college level, every postgraduate level also.
So thank you, Professor Dr. Gupta. So it is now almost time to wind up. Finally, if anybody wants to make any comment, suggestion, otherwise we'll conclude now. So I don't see any hand. So thank you very much.